Hi, everyone. My name is Francisco Lagunas Vargas. I am currently a postdoc at Argonne National Lab. I'm a former member of the nanoscale physics group at the University of Illinois, Chicago, and I'm actually an incoming faculty member at Washington University in St. Louis. So the work that I'm going to be talking to you today is about a family of two-dimensional materials called h-MXenes, and some work that we did using in-situ STEM in order to form a type of defect found in layered materials. Before I continue, though, I want to acknowledge Robert Klee, who was the leader of the nanoscale physics group at UIC, and under whose supervision I was able to complete this work. And without his guidance, we wouldn't have been able to have completed this. So if you haven't heard of h-MXenes, they're a family of two-dimensional materials that were first synthesized in 2011 by a group at Drexel University. But they found that if you take layered max phase materials, so that's a hard ceramic, you can selectively etch away one of the metals in here, like in this case, aluminum. And as a result, you'll see these stacked sheets that look something like an accordion, like in the SEM image shown in the advanced materials cover here. So typically, to etch away this aluminum layer, you need to use very strong etchants, such as hydrofluoric acid. And when you use HF, you cover the surface of these new sheets with fluorine, oxygen, and hydroxyl surface groups. Now, there's a lot of interest in being able to move beyond those particular types of surface groups because researchers have shown that, or have predicted, that if you can selectively pick different surface terminations, you can actually start introducing some new material properties. So that's kind of where my work came in. So I worked with a group at the University of Chicago where they used a novel synthesis route in order to produce h-MXenes with a variety of different novel surface group terminations. So in this little map, or this periodic table where you see the design space or the chemical space of these h-MXenes, in yellow you can see the different types of surface groups that are possible. And we have a paper published in 2020 in Science where we introduced sulfur, selenium, bromine, and tellurium terminations into these h-MXenes and saw some really interesting changes into their properties. So I refer you to that paper if you're interested in more. Some more recent work that we've been doing is not just introducing single types of elements on the surface, but instead introducing organic surface groups into the surfaces of these h-MXenes. And that's really exciting because organic material has a really large design space with just using a few building blocks. So for example, just using nitrogen, carbon, and hydrogen, and oxygen, we were able to introduce all of these different types of organic surface groups, such as alkylamines, diamines, aromatic amines, and so on. So these hybrid h-MXenes themselves were pretty interesting. So we observed some interesting optical phenomena in IR spectroscopy. Specifically, we observed a Fano resonance, which is a result of the coupling between the vibrational states of the organic material on the surface of these h-MXenes and the continuum states in the Ti3C2 lattice. And we also saw some practical improvements to these materials, such as an improved resistance to hydrolysis. And again, if you're interested, I'll refer you to this paper. This paper is really showcasing the fact that we can synthesize these materials and talking a little bit more about some of their fundamental properties. Now, my work as the microscopist is to try to conduct high-resolution studies of these materials to really understand their properties and defects that occur in these materials with high resolution. So to study hybrid materials is a little challenging in the TEM. And this is primarily because the two damage mechanisms from the electron beam onto the material are knock-on damage and radiolysis. And each one of these types of damages is more prominent in a different part of the h-MXene. So for example, knock-on damage occurs when the electron beam comes in and ionizes atoms in the material. And this is expected to occur more in the Ti3C2 lattice, in the h-MXene part of it. However, radiolysis occurs when you start breaking bonds between molecules, and this is expected to happen more severely into the organic surface groups of these hybrid materials. The challenge is kind of finding a sweet spot where you can mitigate both of these damages. Because typically, if you want to avoid knock-on damage, you go to very small accelerating voltages. However, at lower accelerating voltages, you see an increased effective radiolysis. So you would typically go to very high voltages to avoid radiolysis, but then you're going to be worried about knock-on damage. The other thing that we can work on, or that is a careful consideration, is the amount of electrons that we put into our sample. So both of these degradation mechanisms are driven by the number of electrons that we put into it. And so we want to have enough electrons so that we can get as much structural information from a material, but not so many that we're actively changing the structure of it. And then finally, as I'll talk about in the in situ aspect of this work, is we can play around with the stability of the material by changing the local environment. So in this case, we can reduce the temperature of the sample and therefore try to mitigate some of these damage effects. So the first task was to try to acquire high-resolution images of these materials and try to understand their behavior at various dose rates. So this is I used axon dose, which was very helpful because finding these materials in an appropriate zone axis, aligning everything, tuning everything, and then start imaging can be a little challenging, especially if you have to then consider dose. So the fact that this is monitored on the fly is incredibly useful. So you can see from these images at about 1,000 electrons per angstrom squared, we have these nice layered material. So this is our hybrid MXene. And you have those bright regions, which is your titanium columns. And then between those bright regions, those bright bands, we have a dark region, which is where we expect the organic surface group to be. We can see that if we give it a lot more of dose, so in this case, 6,000, 1,200 electrons per angstrom squared, we start seeing this modulation in the Ti3C2 layers, which I marked by those little arrows. And this is kind of the first signs that we see that we're really starting to damage the organic surface groups. And then as a return, or as an effect, the MXene lattice itself is starting to deform. And we can see that seen a lot more significantly at very high electron dosages. So in red here, we have a scan that we did at 20,000 electrons per angstrom squared, way more than you would ever do during imaging, but really just to show kind of a proof that the electron beam will come in, really just alter the local structure of your material. And we can even see some loss of crystallinity, which is more likely than not, we're knocking out atoms and reducing the local crystallinity of the material. So we played around with these materials a little bit more, and we found that if we were to image them at around 2,800 electrons per angstrom squared, we don't really see many effects upon subsequent scans. So you can see here I have scan 1, 2, and 3. And for the most part, these all look very similar. So using that, we started looking at, or using that, we kind of defined our working range for these different MXenes at room temperature. And we started looking at MXenes with a variety of different surface group terminations. So here I show propylamine, butylamine, and dodecamine MXenes. You can see the organic molecule next to the image itself. And in general, we saw pretty much what we would expect. So the larger the surface group, the larger the spacing between the MXene layers. And then the larger the spacing between the MXene layers, we also began to see these slight little bumps or modulations in the spacing between these MXene layers, or the basal plane spacing between these MXenes. So we can go ahead and start getting some statistics about that. And if we measure this basal plane spacing for these different MXenes, we start seeing that maybe things are not as what we thought. So if you see on the bottom here, we compared our STEM measurements of this basal plane spacing with those from X-ray diffraction. And you can see that STEM consistently gives us smaller spacings compared to XRD. So even though we didn't expect to see any changes, or we thought we had found the appropriate dose threshold for these materials, it's clear that something is already happening. And to try to resolve that, or try to figure out what the issue was, we turned to core loss eels. So in core loss eels, you can not only see whether or not you have your carbon or titanium or oxygen present, but based on the fine structure of your carbon K edge, you can actually see different transitions that are induced by the electron beam and correlate those to the bonding of your material. In polymers, this is really well understood, and we should expect to see different types of bonding based on the amount of carbon double bonds, carbon-hydrogen bonds, carbon-carbon bonds, and so on. So here's on the left here, what our first pass was when we started looking at these materials. There is the bare MXene, which is one without any surface groups. And so the carbon signal should only come from the titanium carbide. And you can see we have a peak around 286, and then a broader shoulder that extends with its maximum peak around 296. Or sorry, the 286 is the first peak, and then the broader second peak is around 296. And then we would expect that the spectra from the hybrid MXene would show this bare MXene peak overlaid with additional peaks coming from the organic surface groups. However, as you can tell from the comparison of the two, there really isn't any additional carbon bonding that's present here. And what we suspect is happening is that at these dose rates, we are actually amorphizing the carbon surface groups. And instead of having additional fine features, we just kind of overlay this amorphous carbon peak onto it. And using a little more precise or careful dose or correlating dose with our structural information of these MXenes, we began to understand what was happening. So at 10 electron spangstrom squared, we can see we can just barely resolve the spacing between these MXene sheets. Definitely can't do atomic resolution, but we can definitely get some statistics about the basal plane spacing. And you can see that as we start increasing the amount of electrons that we pump into the sample, we can correlate this with a loss or a decrease in the magnitude of the basal plane spacing. So we go from 29.1 down to 25.4. You'll notice that this effect happens really uniformly across the sample. So it's not like we would see like very localized like swelling of these layers. And here's kind of when we extend this data out into higher dose rates, we can kind of begin to understand what we were seeing in some of the high resolution or the atomic resolution imaging. So once you put the sample into the microscope and you start exposing it to electrons, you see this exponential decay in the basal plane spacing. And this decay begins to plateau around the amount of electrons that we need for atomic resolution imaging. So earlier when I showed that we were imaging these at about 1,000 or 6,000 electrons per angstrom squared, we had already saturated this signal pretty far. And so that's why it looked like the MXenes were really stable, although they were already amorphized. So I mentioned some of the tools that we have as microscopists is changing the local environment of the sample. So a common approach for looking at organic materials is to use cryogenic stem, which is where you take your sample, you put it in one of these TEM holders that has a liquid nitrogen tank, and you cool it down to about 100 degrees Kelvin. And at these low temperatures, the material should be a lot more stable under the electron beam. The challenge with this is that you're cooling a big metal rod down to from room temperature up to 100 Kelvin, and the rod itself will compress, and you'll see a lot of thermal drift in your imaging. And then even once the holder itself has reached some sort of thermal equilibrium, you have a pot of liquid nitrogen that is slowly boiling it away. And this boiling will introduce a lot of vibration into your imaging. So I have an image here that I acquired when the sample was stable. And you can see this is the state of the dewar at when I acquired this image. And you can see this liquid nitrogen that's like boiling away. And that's what's introducing all of the vibration that make acquiring high quality STEM images very challenging. What you need to do instead is wait for the dewar to be just low enough that there's still liquid nitrogen in there that can keep your sample cool, but not enough that the vibrations that come from this nitrogen boiling away are impeding your imaging quality. So this takes your window from the time on the microscope that you could use to get high quality data as opposed to being on the microscope for 8 hours and let's say having 6 hours of active time to acquire high quality images, reduces that window down to about 20 minutes. And so you can imagine that these experiments, these cryogenic experiments can be quite challenging. And if you have to keep track of a lot of different things while you're on the microscope, it only complicates things further. So nonetheless, I went ahead and I did the analysis for these materials using cryogenic STEM. And here's kind of a summary of what we saw. So in gray, I have the original measurements we did with traditional STEM at room temperature. In this like dark gray color is the values from our XRD measurement, which we're a little more confident in because the XRD measurement doesn't happen in high vacuum and is less prone to degradation of the material or less damaging to the material than STEM. And then in this dark blue color, we have the new measurement that we did using cryogenic STEM. So as you can see, there's much better agreement between the cryogenic STEM measurement and the XRD measurement compared to our original room temperature STEM. This method has its limitations. So here I kind of draw a line where if we take a material that has a basal plane spacing below 20 angstroms, then we tend to be able to preserve it using cryogenic STEM. However, if the spacing is much larger, it's likely that vacuum effects, so the high vacuum in the column, will damage the material, or the material is just a lot more sensitive to the electron beam, where we still can't quite see the same spacings that we expect to see in XRD. So either the material is in this preserved region or it starts approaching this degraded region, even in cryo-STEM. But if we look at samples that we expect to be preserved, then we can go back to our EOS measurements and start getting an idea if we're able to detect differences in the bonding. So here is our BUA sample, which is composed of a lot of carbon-hydrogen bonds and carbon bonds. And you can see in red is the spectra that we acquired at room temperature, and then blue is the spectra that we acquired at liquid nitrogen temperature. And clearly there's a lot more fine structure, much better signal quality at cryogenic temperatures. We can quantify this, which is pretty exciting. So if we look at two different hybrid MXenes at cryogenic temperatures, their spacings show us that the material should be preserved at low temperatures. And we look at ones such as butylamine, which is the one with a lot of carbon-hydrogen bonds and carbon bonds, and compare it to spectra from our benzylamine terminated MXenes, which are also composed of carbon bonds and carbon-hydrogen bonds that also have carbon double bonds. Then we see this difference show up in our comparison of the carbon K edge. So here is our benzylamine terminated MXene and our BUA terminated MXene. And you can see between this 285 and 287 region, this profile is a lot more flat compared to the BUA sample. And we suspect that arises due to the differences in the carbon double bonding and the carbon hydrogen bonding present in each of these materials. So that's really exciting. We're seeing directly signatures of the organic material. Okay, so now we can talk a little bit about some of the defects that we see at room temperature, or in these hybrid MXenes at cold temperatures. So a couple of slides ago, I showed that if we're imaging with enough electrons to acquire atomic resolution imaging, the materials don't really look that different from what you would expect. You have these layered structures, and between them, you have these dark regions with your organic material. And if we put a lot of electrons into it, maybe we can start seeing some small modulations, but we don't see anything very dramatic. So what happens when we look at these same materials when they're starting in their pristine condition, and then we start breaking them down with the electron beam? Well, so pause this one on the left. If you could focus on the middle one, this is us looking at a MXene that had started in its near its basal plane spacing that we measured in XRD. So we expect it to be in its pristine state. And then as we start applying more and more an electron dose, you can start seeing the material degrades in this really like significant fashion. So I'll pause it right here. So you can see the formation of all these different little Y defects, like where it would go from one layer to two layer. It looks like a little Y fork. And then this effect is actually quite reproducible. So here's another region in the sample that we did it. And you can see we're increasing the accumulated dose in the sample. You can see there's a little bit of wiggling that's happening. And then if we zoom out, we can see we've clearly affected the material or the structure of this material in a pretty significant way. So what is happening? So we went through the literature. We tried to see if anyone else had seen similar effects to us. And we came across this paper in Nano Letters where a group had used a mechanical indentator to basically perturb these molybdenum sulfide 2D materials. And they formed these little ripples that propagated through the material, which they coined the term Ripplocations. And if we look at our images and the images that they acquired from their replicated materials, we can see that these show they resemble one another quite strongly. So what is a replication? So in 2D materials, in 3D materials, we know about a variety of different types of like structural defects. One of the common ones is where you have like a locally inserted layer, a locally inserted column of atoms, and you have this dislocation defect where you have this, so you go from, because of this locally inserted atom, you have this strain that occurs on this material, and these dislocation defects tend to repel one another. In 2D materials, you can imagine that if you locally insert an extra column of atoms, what's going to happen is, since these layers are free to move around, you'll introduce this buckling that occurs between these layers. And you see this ripple-like defect, and thus the term Ripplocations. So why were we not observing these at room temperature? Well, as you can imagine, you have these layers of your 2D material separated by organic surface group. And as I showed, we at room temperature are amorphizing the surface group and in effect locking in the MXene layers. Whereas at liquid nitrogen temperatures, the MXene layers, once we start degrading the organic surface group, we can start introducing different strain in the material that will then lead to the formation of these different types of Ripplocations. So there's a lot of work where people have done like computational modeling of the motion of these Ripplocations in 2D materials. So here's one where a group did a molecular dynamic simulation of Ripplocations in graphene. And you can see their movements that they observe tend to match what we see. And you can also see that the effects of local like vacancies in the material lead to this tearing-like effect, which is what we think is happening. So as you accumulate enough electron dosage, you're knocking out titanium atoms in addition to destroying the organic surface groups. And then you have these Ripplocations that are migrating to those defects, where then you end up having this really altered structure in the end. Here's probably one of my favorite slides. So the field of the study of Ripplocations has really started growing in recent years. And it's because it has significant implications to a variety of different material systems. So in this paper published in Nature Communications, they were talking about the impacts that Ripplocations can have in the lithosphere, which is one of the layers in Earth's core. And they have a little graphic here where you have this Ripplocation that's induced from some C-axis strain, and then they say moves laterally like a ripple to the right. And going through or observing these Ripplocations in the stem, we were actually able to do something very similar to what they described. So here's a benzylamine terminated MXene, and we can see a couple of Ripplocations that had formed just based on the geometry of the sample. And then when we go in and start trying to image these Ripplocations, we can see that this Ripplocation starts out about 40.4 angstroms away from this terminated layer here. And then on the subsequent scan, we see it migrate over to the left, moves laterally like a ripple to 26.7 angstroms. So that's really exciting that we can see the movement of these different types of defects in the TEM. To conclude, the fact that we're able to see these Ripplocation defects at these scales is really incredible, because this type of defect has been described or has been used to describe like material systems or defects in material systems in over 10 orders of magnitudes spatial scales. So here we're looking at it at some of the smallest possible like mechanical scales at, between 1 to 5 nanometers. But you can see we observed similar things in fib lamella that we made of these samples that are on the terms orders of 100 nanometers. There's people that are studying these types of defects in like just layered like playing cards. In this case, they have these metal cards that are stacked on top of one another, and then they indent it, and we can see the formation of these Ripplocations. And then, as I hinted to earlier, there's these types of ripple-like features that occur in Earth's core mantle. So it's really a defect that is just everywhere in these layered material systems. Okay, so to wrap up, I just want to acknowledge all of the people that have helped with this work, that have given me feedback or have contributed in the form of samples. Of course, the team at Argonne National Lab, Zachary Hood is my PI there, and he's been really supportive of a lot of this vaccine work. Of course, Dr. Robert Klee at the Nanoscophysics group, and then Dr. Talafine at the University of Chicago. His group actually makes all these materials, and we were able to find this interesting defect because of it. And of course, all of the funding sponsors, and as well as Protochips for giving us access to axon dose and axon synchronicity, which made a lot of these kind of heroic experiments a little easier. Great, thank you.